Just a reminder, you have homework 20 that is due after break. I looked a little more closely at preparing 6. I thought I covered the whole chapter, only covered the end of the chapter. So if you haven't done it yet, I'm going to move the due date to the Tuesday after break so that it's a little closer to when we're actually covering that. We will have a quiz on the Wednesday after break and a exam on the Friday. I may make the quiz like a Canvas quiz or a take-home quiz. Just kind of have those things in mind. Quiz covering chapter 6 primarily. The exam mostly on chapter 6. I might pick up a couple of threads on things that were sort of cross-cutting themes. I'll talk more about that. Okay, so we had been talking about light having wave properties, and we calculated the frequency of light. And what we wanted to do was establish how we know light is a wave. And so waves do certain things, and we are going to look at whether or not light does those things. So one of the things is light refracts, which means that it slows down when it enters a new medium. So the medium is whatever it's traveling through. So if it goes from the air through glass, it's going to slow down. Or really, it's more accurate to say it changes speed, because if it goes from glass to air, it will speed up. So when that happens, it tends to change direction, because as the rays of light come in, they're hitting at different times on an angled surface, and it causes it to change direction. We'll just say it changes direction. So if you want to look at an example of this, in the baskets on your tables, there are beakers with water. You can put in a stirring rod. And if you do that and look from the side, you should see that it either looks like there is a break in the stirring rod, or it looks like the stirring rod is sort of bent. And so that is a consequence of the light changing speed as it goes from the air to the water, from water to the glass. Okay, so this is actually what gives us rainbows, and that is going to be this picture up here is kind of an example of that. I meant for it to be lower down, but anyway. So as it goes through a prism, which is normally like a glass or plastic triangle, we get a little rainbow on a wall or something. This is kind of the way raindrops work, but I'm going to explain with the triangle first. So we've got the light hitting this at an angle. Now, if it hits straight on, you don't see a lot of change in direction. It's only when it's hitting at an angle. And so the light that goes through the smallest amount of that triangle towards the peak is only slowed down a little bit. And the light that is further down goes farther and is slowed down more, or slowed down for a longer amount of time. And so as they slow down more, the path bends more. And so you get the colors spreading out. And so that's kind of what that's illustrating there, is the colors spreading out. Now we'll come back to that image later. Okay, so light spreads out. Light changes direction when it goes through a different medium, and we get rainbows. And so light is behaving like that. Now, if we think of a raindrop as a circle, now sometimes we think of it as kind of like teardrop shape, and that's actually not the shape of raindrops. We found that they're actually pretty spherical even while they're falling. But you can see how like the top part might be a very small distance and the middle part might be a larger distance. So depending on which part of the raindrop you're going through, you might slow down more. Have in your baskets there a little square rectangular type thing like this, might have different colors on it. And I'm gonna hand you a laser pointer. And so the first thing I want you to do is just point the laser pointer at the desk so you can see that it's forming a dot. should be able to see a green light on the screen there. And if I put this slide in here, now that green light turns into several dots of green lights. That's that diffraction pattern of big spots and little spots. Okay. So we have established that light is behaving as a wave. We call these waves electromagnetic radiation. So if we think about water waves, ocean waves, the thing that is waving is water. There's physically more water molecules up high or down low based on where the wave is. For light, there's no physical object there. So what's changing is what's called an electric field and a magnetic field. So what that means is that if I have an electric field, then a positive charge is going to feel pulled in one direction or another direction. And it might be a slight pull, or it might be a really strong pull. So that's how big the field is. So this kind of tan area is kind of showing how that strength of that pull is very little when it's close to this midline, and it's very strong in this direction when it's down low, and it's very strong in this direction when it is up high. Simultaneously, there's a magnetic field. So same idea, only the magnet is being pulled towards the North Pole or the South Pole. So the blue here, or the darker color, is showing a very weak magnetic pole, a very strong pole towards the north, weak pole, strong pole towards the south as it goes back and forth. Okay, that's hard to wrap your brain around. If you can't, just understand that when I say electromagnetic radiation, I mean light. Okay, so I'm going to use EM radiation and light kind of interchangeably for the next couple of weeks. All right, so there are several kinds of electromagnetic radiation. The ones that are going to be important to us, and the stuff that's at the top of the slide you've already written down. I had it earlier, so you don't need to worry about it, but I'll put it there then. But what I want you to know from this slide is there are 7 types of electromagnetic radiation. So you should know their names and what their order is. And so that's given here. Low end, we have radio frequency. High end, we have gamma rays. And then for the middle ones, I want you to know what happens when an atom or a molecule is hit by this kind of light. So first of all, what this is saying is that microwaves in your microwave oven is exactly the same stuff as visible light. Ultraviolet light that can give you a tan or cause skin cancer, that's the same stuff as visible light. X-rays for your teeth, that's also the same as visible light. They just have different frequencies and energies and wavelengths, but it's the same kind of thing. Okay, so radio waves, as you might imagine, are used to transmit radio signals, also television signals. Sometimes remote control devices work through radio frequencies as well. So there's some applications there. Microwaves, when matter is hit by microwave radiation, it takes molecules and causes them to spin, particularly polar molecules like water. Now, if I had just one direction for my wave, like if it was always positive, then it would just keep spinning in the same direction. But the wave is going back and forth. And so the molecule starts to turn in one direction, but then the wave changes. And so it starts turning back in the other direction. So you get this kind of shifting back and forth, side to side sort of thing. And that motion leads to heat. So remember, thermal energy was the motion of the molecules. This turning of your water molecules in your food is what's causing it to heat up. Okay, so microwaves cause molecules to turn. Infrared, sometimes we call this heat, which is odd because microwaves are what we think of as heating things, but infrared light actually causes molecules to vibrate. So this is a kind of motion where the molecule itself, the bonds get longer and shorter. So if my hands are atoms, my head is an atom, my arms would be the bonds getting longer and shorter. Here, I'll show you on the screen what I'm doing here. So this would be like a vibration. And depending on what the frequency of the light is, they might just have a slow vibration, or they might go really fast, okay? So infrared light causes molecules to vibrate. Now, again, that's a kind of motion, which leads to heat, which in turn, we might be able to interpret through, say, infrared vision goggles. So the electronics of the goggle takes that reception of the infrared radiation and changes it to a signal that our eyes can see. All right, so visible light and ultraviolet light do the same thing. X-rays are very similar. So visible light and ultraviolet light is what we talked about on Wednesday. The electron moves from close to the nucleus to farther away from the nucleus. And it could be an outside electron, it could be an inside electron. It really depends on what the atom is, what the element is. But it's basically moving the electrons around. And as the electrons move farther away, they're absorbing light. And as the electrons fall back into place, get closer to the nucleus, they release light. And that's true for both visible and ultraviolet. X-rays, basically the same thing, except for they get so much energy, they're just peeled right off. Okay, so when you take an electron away from an atom, you are turning it into an ion, right? It becomes charged. You've removed a negative, so now the whole atom is positive. So X-rays are called ionizing radiation, and they can be dangerous because if you have a lot of molecules in your cells that have had electrons ripped away from them, then they can start reacting as ions would, trying to gather electrons from other places, which can cause kinks in the DNA, which might lead to cancer, or it might cause damage to the cell membrane or the parts of the cell, which would cause the cell to say, oh, danger, warning, and then blow itself up. So that's why you don't want to be exposed to too many X-rays. Gamma rays basically are so intensive that they just kind of shred atoms. So this is what you would be exposed to if you were a space traveler. And so when they build the space station or rocket ships or whatever, they have to incorporate into the design protections to block out some, they can't block out all of it, but some of the gamma rays that are coming from those. Okay, so microwave spin, infrared vibrate, visible and ultraviolet move the electrons, X-rays steal the electrons.
We are going to get back to talking about light, and today we're going to talk about how light tells us something about electronic structure. I can get the computer.
Okay, so we talked about some different ways that we know light is a wave. We talked about light being something that it doesn't bend so much as it changes direction because it slows down when it goes from one medium to another. So medium is what it's passing through when it goes from air to glass or from glass to water. And that's why when we put our stirring rod into the glass of water, it looked like it was broken. So there's a lot of evidence that Newton gave us and others that light is a wave. But in the 20th century, technology evolved in such a way that we developed some things that helped us to see, you know what, there's some problems. And so light should behave as continuous. We said that was one of the characteristics of a wave. It shouldn't behave as if there were individual units of light. And these three different effects are going to be things that actually show that light is kind of behaving like it has particles. The first two we're not going to go into a lot of detail on. I'm just going to introduce it enough so you know what the terms mean. But the last one, atomic spectra, is really going to lead us into electronic structure. So those are the things that we will be focusing on.
right, anybody still need this? Yep. Okay, so the first one we said was black body radiation. And basically what black body radiation is the idea that when you heat something up, it starts to glow. So you turn heat, which is a thermal energy, into visual radiant energy. And so you've seen this kind of thing before. If you've ever had a campfire, you've seen burning embers, that, you know, even after the flames are gone, the embers are glowing. If you've ever used an electric stove, the burners, when they get really hot, will glow red or orange. And then older light bulbs, incandescent light bulbs, work on this idea. So more and more we're switching over to fluorescent light bulbs. And the reason for that is that the energy, electrical energy that we put into an incandescent bulb, a lot of it goes into just heating the bulb up because that's how the light is produced. So you lose a whole bunch of the energy that you put in just because the bulb is hot, and you only get a little bit of light out. Whereas with a fluorescent bulb, there's a different mechanism for how we get the light. And so you're not losing as much electricity, or rather you don't need as much electricity in order to make it glow. Okay, so that's the basic idea of black body radiation. Why this becomes a problem is a little bit complicated. So I'm just gonna do a little bit of hand waving here, but it's gonna lead us to an equation that we're gonna use. Does anybody still need this slide? Okay, so we had talked about how amplitude, the height of the wave, should correspond to the energy. And so kind of connected to that is this idea that black body radiation, we should be able to predict the wavelength based on the temperature using this curve here on the right, the purplish one. That curve just goes up. It never comes back down. But when we have black body radiation, we actually end up with a curve more like the smaller one, the inner one. And so the shape of that curve is best explained if we have light only being emitted in certain energies. So how we get from A to B is complicated math that I'm not going to go into. But we have Planck, who was one of the famous scientists at the time, came up with this equation. E equals NH nu. So N is how many individual pieces of light we have. And then H is a constant. It's called Planck's constant because he was the one who came up with it. And then nu, the thing that looks like a V, that is the same thing from our other equation. So what was that in our other equation? Anybody remember? So we had speed of light, we had wavelength, and we had frequency. Which one was it? No takers. That was frequency. So his constant is 6.626 times 10 to the negative 34 joule per second. So this says an individual little piece of light, which we're going to call a photon. An individual photon doesn't have very much energy. But in order to see anything, we need a whole bunch of photons. When we use this equation, we're basically just going to assume there's always one photon. We're going to assume that that n is always going to be equal to 1. Okay, so big important equation. Make it bigger and more important. So we'll use this here in a second. You're also going to want to go ahead and write down H because I'm going to have you plug this into a calculator. If you have your calculator, go ahead and pull that out. So we're going to look at this question. What is the energy of a photon, so just one of them, that is from a red laser pointer. And remember, on Wednesday, we calculated for that particular red laser pointer with the lambda equal to 650 nanometers. We found the frequency was 4.6 times 10 to the 14th hertz. And hertz is just another way of saying 1 over seconds. So we don't need lambda for this. We're going to use the NH nu. N is 1. H is the number from the previous page, and nu is what we've got here. So we're just multiplying H and the frequency together. Okay, and if you finish jotting that down, try plugging it into your calculator. Okay, if you have a graphing calculator, it's going to work a little bit differently than these calculators do, but a lot of times people will grab these calculators. So I want to show you how to do scientific notation on this. So when we do Planck's constant, 6.626, was it? That part we call the base, and then we say times 10 to the negative 34. So if I put this in 6.626, one thing I can do is I can multiply by 10, and then I can say this x to the y here is how I do an exponent, so to the. On these calculators, if you're ever using these, you have to do the number first and then hit this plus minus button to change it to negative. So you don't use the minus sign over here, you don't use the subtract. You just use this plus minus sign. So when I hit that, that's going to tell me what I just typed in. And you'll notice there's nothing in here that says times 10 to the. It just gives the base part and the exponent part. So you'll have to learn to read on your calculator, and a lot of graphing calculators will display it like this too, that when you see the little exponent there, that's not saying 6.626 to the power of negative 19, it's saying 6.626 times 10 to the power of negative 19, okay? There is another way that you can do this, 6.626, and then this little EXP button down at the bottom, that means times 10 to the. So you don't have to do times 1, 0, and then find the XY, but you just hit this. And you'll notice the zeros appear here. And again, you type in your exponent and then the negative. So that's another way to do it. If you have a graphing calculator, instead of EXP, it usually says capital E, capital E. Sometimes you have to do shift to get to it. So that's another way to do that. If you do it that way, it will keep the whole number together and you don't have to worry quite as much about parentheses. But you do have to remember that you have to pick one. You can't do this button and do times 10 to them because you'll get the wrong answer. So we know what this is supposed to look like. If I do 6.626 EXP and then do 10 to the 19 negative, I get 0, right? So I can't do both. I can either do times 10 or I can do EXP. And that's a common mistake I see on calculators.
And if you're ever in a test and you just want to make sure that you're doing it right, feel free to come up and ask me about that. Okay, so anybody come up with a good answer there?
I put in the wrong exponent on the calculator because I was thinking of the answer here. We should have gotten 3.0 times 10 to the negative 19. So I should have put in negative 34 on the calculator.
But yeah, you'll end up with times 10 to the negative 19. And just like we said, positive 14 was a common exponent for frequencies. Negative 19 is a really common exponent for energies. So negative 19, negative 18 are both real common energies. All right. That. Our second, oh, I skipped something here. Found the, oh, no, we didn't. Okay. So the next question is, if we have a certain energy, so this one is to the negative 18th instead of negative 19th, if we have a photon that has a certain energy, can we get back to the frequency? So again, this is our equation, and we have one electron. So what would the equation look like when I solve for the nu, which is the thing that looks like V? I would have V is equal to what? We're going to leave E where it is, right? E divided by NH. And then we said one photon, so this is just going to be 1. So it's basically E divided by H. Okay, so we're going to take the energy that was given there and divide it by this number here. And dividing by scientific notation is where a lot of people end up messing things up, because you got to keep that times 10 to the negative 34 with the other part, the base. So put it in parentheses when you plug it into your calculator. All right, so give that a go, see what you get. All right, does anybody have an answer yet? What do you got?
2.6 times 10 to the 15th.
All right, so Ian says 2.6 times 10 to the 15th. If you were to make a guess, and that is correct, if you were to make a guess based on the exponents, that is the only exponent that is anywhere close to the exponent that I said frequencies usually have. So if you had plugged into the calculator and got something else, you might have been thinking, maybe I should recheck how I plugged things in, okay? And if you are getting one of those other numbers, try plugging it in again until you can get the right one. And if you can't get it, make sure you either check with me, or if you're checking at home, check with somebody else. How do I get to this number? How do I plug this in? All right. So the answer is C on that one. Okay. So our next problem with the waves is called the photoelectric effect. This is what Einstein got his Nobel Prize for. So the photoelectric effect is basically the idea of how solar panels work. That if you shine light on a solar panel, you get electricity out of it. And that's, nothing unusual, because, we already knew that light was a kind of energy. But how it happened is what causes the problem. So I'm going to zoom in on the surface there. Actually, let me go back here. So what's going on in this picture is this is the solar panel in the back. It's absorbing light. And then when it gets enough energy, it pops an electron off, which is attracted to this. It's positively charged, and the negative electron comes over here, which goes through a circuit and creates electricity. So we're going to zoom in on just the solar panel part.
So that thing that was vertical before, I've got it horizontal here because it was easier to draw this way. But we've got light coming in, and the light comes in, hits the electrons pop off. And what we expect to happen if light is behaving the way waves should is the brighter the light, the more energy that's coming in, the more electrons you get to pop off. And that is exactly what happens. However, what also happens is that when you have that cutoff of enough light, depends on the frequency. So red light, you would need it very intense, but with purple light, even a very dim light would cause the electrons to pop off. And so there was nothing about the wave nature of light that led people to believe that energy should be dependent upon the frequency. And so that's kind of the connection that we're looking at there. And so that's tied back into Planck's constant as well. So the big picture on that one is, at the bottom there, energy depends on the frequency as well as the amplitude. Okay, so Wednesday we said amplitude was related to energy. Now we're saying frequency is also related to energy. Okay, so our third third problem is the problem of electronic spectra. And this is what we're going to focus on because this is what's going to tell us about the electronic structure of the atom, where the electrons are in the atom. So we know Rutherford came along, proposed the nuclear model. We got the positive in the middle. We got the electrons on the outside. We know that this leads us to that solar system model where we've got the orbiting electrons. But it does kind of beg a question. Well, why do they have to be on a particular path? Why can't they be at any orbit? You know, and why can't we have an electron that is a few nanometers further out from the nucleus? Actually, it would have to be picometers, not nanometers. But in any case, why can't they be on slightly different paths? So first, we have to ask ourselves, well, how do we know they're only on particular paths? So I'll let you guys catch up here before I move on with that. So in your baskets, you should still have those things that look like little slides with a plastic window in them. And there's only one or two baskets per group, so if you're done, you can pick up. I want you to look out the window through the light. Probably the tree being in the way is going to be problematic. So let's look out this window over here.
Where's the window? Now what happens when I do this?
Flip it like backwards. Doesn't matter which side.
It shouldn't. There's the rainbow. So those of you at home should be able to see a rainbow on your screen now. So the sun is a black body radiator, which means that what is causing the color is heat. And the heat kind of forms that curved path. It can be any color of light. Now, if you take these same things and look at the fluorescent lights, you're going to get streaks in your pattern. Now, you're also going to get the pattern of the lights themselves. So we're going to take a look at the bulbs that we have here at the front of the room. So I'm first going to put on hydrogen. Darn things both start with H. And what I want you to do is to take the spectroscope, which is this black box. You want to lay it flat. And you are going to look through the narrower end, have the wider end out in front of you. And you should see a slit. And so what you want to do is get that slit, first line it up with this so you make sure you're in the right direction. But then you're going to move it slightly to one side. So the light won't actually be in the slit. It'll be moved to one side. Now we've got a lot of ambient light in here, and that is going to cause kind of that rainbow effect. But what you should notice is there should be particularly red and green, a really strong line. I can see this So the numbers are so you can measure it. We actually do labs from time to time with that. Let's see. I almost had it. There we go. It's not focusing, but you've got some lines there instead of a full spectrum. So you've got the red line, the green line, and the blue line there. They're kind of blurry, but that's what you should be seeing. So what this is showing us is that we only get particular colors. You don't get all the colors. You don't get orange. You don't get yellow. You only get certain colors. And so what we want to know is, why does that happen? We had this picture. Where are we? Okay, so we had this picture that kind of shows the same thing. So this actually is showing us hydrogen, the red line. Now, they call it green. I always think it's light blue. So if you didn't see green, you saw something that looked more like light blue, that's what they're calling the green line. So we really only see these four, or you might see a fifth purple line in the visible region. And so what that's telling us is that hydrogen is only allowing certain energies. So where are those energies? Let's remind ourselves where that light is coming from. We have our solar system model of the circles. The light that comes in, or energy, in this case it's electricity, is going in, and it's going to push the electrons away from the nucleus. That's the absorbed energy. And then as that electron relaxes back down, it lets out light. Okay, so that arrow leaving is representing the light that leaves when the electron leaves. So the idea is the difference in energy between these two circles determines the color of the light. And if we only have specific colors, then these circles have to be at particular places. They can't be anywhere. I can't have a circle here, 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 and all these spots in between. They have to be at particular energy levels, okay? And so you can't really explain that very easily without saying, light, which we know is a wave, is behaving like a particle. What if electrons, which we know are a particle, can behave like a wave? So this is called wave-particle duality. Everything can either be a wave or a particle. You can also be a wave, but your frequency would just be so high, I think that's the direction that it goes, that it wouldn't be detected. Okay, so if you have an instrument, there's a guitar here, we end up getting our tones by the waves resonating or reinforcing one another. And we get that because we fix the ends of points of the wave. So we attach one end of a guitar string down here, and then the other end is determined by where you place your fingers. If you have a flute or a wind instrument, then it's the length of the tube that determines these things. But the endpoints are fixed, which means you have to come back to the starting point. You can't finish your wave off course. That would be like detaching the ends of the wave. So if I have an electron that is traveling around at a certain distance in a wave form, but doesn't come back to the place that it started, it's kind of like a cut guitar string just flapping around in the wind. Okay, it's not going to do anything. So the electron is a wave, and where the wave is allowed to be is determined by when it can get back around and reinforce itself, when it can resonate. Okay. So on the left, I've got a picture of atoms that are, an atom that has lots of orbits. But it would be kind of cumbersome to always have to draw the whole atom. So what we're going to switch to in this chapter is, instead of drawing the circles, we're going to draw lines. So that innermost line, that is this small line right here, kind of like at the level of the top one here. So if I have a hydrogen atom, it has one electron that fits in that one spot. And if I have helium, it can also fit another electron in that spot. But because that is so close to the nucleus, so small, or that's the easiest way to think about it. That's not the real story of what's going on here, but we only can fit 2. So at the next level out, we can fit more electrons. And so for lithium, there are 3 electrons, and that 3rd electron can't fit in the first layer, so it goes in the next layer out. So the last layer that we have electrons in, we call that the valence layer. These are valence electrons. Lithium has 1. Hydrogen had 1, okay? And that's why they line up in that first column, okay? Now, if I go to beryllium with 4 electrons, it has 2 in its outside layer. Okay, so it's in column 2. Now, helium also had 2. It's not in the same column because we're going to use a different rule for helium. I'll talk about that in just a second. Let's say we go to sodium. Sodium is element 11. So it's going to put in first the 10 electrons, 2 for the first layer, and then 8 for the second layer. So our second layer can hold 8 electrons. And then the next electron goes in the 3rd layer. Okay, so sodium also has 1 electron in its outside layer. Then magnesium also has 2 electrons in its outside layer. So the patterns we see on the periodic table are related to how the electrons are organized in the atom. That's kind of the key thing we're trying to get out of here. Now, for helium, it has filled its shell. So it's all the way over on the right-hand side on the periodic table because those are full. The element right before sodium is neon. It would have 10 electrons. It would have filled its shell. So that's why helium ends up over there. Okay. So you'll notice, let me actually back up a second, that I put a really big gap between our first layer and our second layer, and then a smaller gap to the 3rd layer, and an even smaller gap to the next layer, right? And that's kind of how it is in an atom. So we can think of the electrons as going from, I should give you guys some more light. Going from the bottom layer up, if we absorb energy or absorb light. And this first step, I would say the first step's a deuce. That's a huge step. And then they get smaller from there. But it is important to remember that this first step is bigger than all of the other steps put together. Okay? All right. Let's see. We already looked at that. I don't think I had anything to add there. Okay. So it's actually so big, it's in the ultraviolet. So falling from anywhere to energy level 1, this down here, this energy gap is so big, it releases ultraviolet light because that's higher energy than we can see. All right, so when that happens, we get ultraviolet light for helium. Now, for other atoms, they're going to grow in energy. I'm sorry, for hydrogen. For other atoms, they're going to grow in energy, and we're going to end up having higher energies than that. But for hydrogen, 1 electron falling down to that first level is ultraviolet light. So what we see, those lines that appeared when we looked through the spectroscope, those colors are not from the electrons falling to the first level. They're actually from it falling to the second level. So we're going to kind of see what that might look like. So if I have an electron that is falling from, this is now energy level 3, and it's going to go from 3 down to 2, that's going to let red light go. Okay. So 3 to 2 is the lowest energy of the colors, and the lower energy color end is red. The second one is when we go from 4 to 3. So going from 4 to 3, we get that kind of light blue-green color. Going from 5 to 3, we get the blue color. Okay, so each color, each line that we see looking through that spectroscope corresponds to one change on here, a change from some energy level that's higher to, in the case of helium, energy level 2. So it's falling down to an energy level that we can see. Okay, questions about that? Okay, so our important points. The electrons leap from level to level. They're never in between. So they correspond to the light energy that we just calculated corresponds to the difference in energy between level 1 and 2, level 2 and 3, whichever levels the electron's moving between. And if I put in an energy that's some other energy, that electron isn't going anywhere. The second point says the energy difference between levels grows smaller as n grows larger. So that's where I said when n is equal to 1, our first energy level, the difference between that and level 2 is huge. And then between 2 and 3 is small. And then between 3 and 4 is smaller, so on and so forth. So the energy difference gets smaller and smaller as we get further out. For any given element, I'm always going to get the same set of lines, which is why this gas tube works, because there's a whole bunch of hydrogen in here and they're all emitting light at those specific wavelengths. But if I switch to this light, if you look through your spectroscope at that, you're going to see different sets of lines. So if you want to, you can look over there. And then the last thing is that if light is coming out, that's a form of energy. So it's exoergic. It's not called exothermic because it's not heat that's coming out, but it's like exothermic. And absorbing energy or absorbing light is endoergic. Now we can get this light from running electricity through it, but we can also get it by putting other forms of energy in, such as heat. So you're also going to be looking at what's called a flame test. So if I put a particular element into a flame and it has particular colors, then we're going to see those colors more dominantly. So something that emits a lot of green and blue light is going to look green in the flame. Something that emits a lot of reds and oranges is going to look red or red-orange in a flame. All right, anybody still need this? So one of the elements that you're going to test is going to be sodium. And so when you put sodium in the flame, you're going to get a bright yellow flame. It might not look a lot different from what you think most flames look like. That's because there's so much sodium in the environment. We usually have that. But if I were to look at a sodium lamp, one of these things, what I would see is two really intense lines here. They're called the sodium D lines. Okay. So there is a connection between what you see here and the flame test. Similarly, if I have a mercury vapor lamp, so street lamps tend to be either sodium or mercury. The sodium ones kind of have a purple glow around the outside. Their spectrum would have a lot of purple lines. Okay, so the big picture here is that each element has a unique set of colored lines. So this is how we can look at stars and say, oh, this star has a lot of hydrogen, this has a lot of helium, or this one actually has some carbon and oxygen in it as well. Orbitals are basically where the electrons live. So those circles that we drew, those kind of represent the orbitals.
each orbital can only hold 2 electrons. So our first orbital was just 1. The second circle was actually made up of 4 orbitals. Okay. So we identify those with the quantum number n. N just tells us which level we are at, how far we're away from the nucleus. Okay. And so when I say n equals 1, there is 1 orbital and there are 2 electrons. But at n equal 2, we actually have 4 orbitals and 8 electrons. And so the reason that we can have 4 is that the energy levels, n equals 1, equals 2, n equals 3, have what are called sublevels. And those sublevels correspond to the shape of the orbital. So we draw them always as circles, but they actually have some different shapes. And we'll talk more about this later. P is kind of a dumbbell shape. D is kind of a 4-leaf clover shape, but they all hold only 2 electrons. Okay, so the other thing waves do is they diffract. So what this means is that if you confine them to a narrow space and then take away that confinement, they're going to spread out. So if we think of this as being waves from the ocean coming in and hitting a wall, maybe a barrier wall, but there's a little boat in or little hole in the barrier wall so boats can get in and out. When those waves hit this wall, if the wave is over here, this part can't do anything except for bounce backwards. And so that's what it does. But the part that's here is going to go through the hole. Now, if I had particles that I was doing the same thing, if they hit away from the hole, they would just bounce off. And if they hit the hole, they would go through. But the particles would just keep going in the direction they were going. They wouldn't change directions. Waves, on the other hand, start forming these curves and fanning out. And that's exactly what light does. So one way that we can tell is that when we have multiple splits, so if we had a hole here and a hole here, which you'll see on the next slide, those curved portions would start overlapping, and that would create a pattern. Does anybody still need this slide? Okay. So this is showing 2 holes here, and we've got a set of curves that are kind of centered around this top hole and a set of curves centered around the bottom hole. And what you notice when you look at the waves is there's a regular pattern to where they're overlapping. It's not just willy-nilly crisscross anywhere, but we have a straight line here of big gaps, and then kind of an area where the lines are close together again, and then we have bigger gaps. So those correspond to what we call constructive and destructive interference. So basically, when the 2 waves come together, if they're both trying to push the water up, if this is a water wave, if they're both trying to push the water up, then it works really well when we get a super big wave. If they're both trying to make the water dip down, then it dips down really far. So that's constructive interference. They're reinforcing one another. But if the waves are coming together and one of them wants to go uphill and one of them wants to go downhill, they just sort of cancel each other out. And that's called a node. We'll get back to nodes after Thanksgiving break. And so what we have going on here is we've got sections where we've got a lot of overlap and constructive interference, and we get a lot of the wave. Now, if this is light waves, that's going to show up as a bright spot, a lot of light coming through. Where they cancel each other out, the destructive interference, so this is where one is going up and one is going down, they cancel each other out, we get a dark spot. The light cancels itself out. That is a diffraction pattern. So what I want to do, oops,